Hello all, this is Prabhat and this is my project presentation for the course Machine Learning for Image Processing. So this is the outline of the presentation. First I will talk about the problem statement and how I modeled the problem. Then I will talk about data pre-processing and the network that's used in this project. I will also talk about an alternative model called Voyager, which served as an inspiration throughout the project. I will finally end with stating my observations and the summary of my work. So the problem statement is to build a machine learning model for data prefetching. This is an interdisciplinary project that requires knowledge in both computer architecture and machine learning domains. So what exactly is data prefetching? Simply put, it is the process of fetching memory needed by the CPU before the CPU asks for it. So this makes the CPU more efficient by removing or reducing the time delay that it takes to wait for the memory to be fetched. The component that performs prefetching is called the Prefetcher. And to create a machine learning based prefetcher, we need to train the model with some input data. And this data is given in the form of trace files. Traces are memory addresses that are arranged in the order in which they are called by the CPU. The format of the trace address contains the unique instruction ID, the cycle count, the load address, the instruction pointer, and the LLC hit or miss. So we can use a portion or all of this data to predict the future addresses. So this is an example of 100,000 addresses in a trace file, and this is a plot of that. And this is a plot of the offset addresses corresponding to these load addresses. Offset address is a portion of the load address that contains most of the pattern information. Since the order of the data matters, we can model this data as a time series prediction problem in which we feed in sequential data and we try to predict the next item in the sequence. I can broadly think of two kinds of models for this problem. One is a classification based model which separates each possible load address into a different class. It converts the inputs as one hot encoded tensors and the outputs as probabilities corresponding to an address. We can also think of a regression based model which maps a load address into a format that is convenient for the machine learning model to process. The output is remapped to get back the load address. So we use recurrent neural networks for the model to take in the time series data. And also we must note that each trace file has different access patterns and the model needs to adapt to these patterns quickly. For this purpose, we use online training where a portion of the trace file is used to train the model while the rest of it is used for testing. So let's talk about how the data is pre-processed. Each load address is split into something called the page address and the offset address. Number of possible page addresses are very few. The number of offset addresses can be up to 2 power 20 and there are a lot of offset addresses. So after we split, we follow different approaches for classification and regression. For classification, we create one hot encoded tensors for each possible combination of a page and offset address. Alternatively, we can also use embeddings which consume lesser memory footprint and lesser computational resources to process than the one hot encoded tensors. For regression, however, we convert the load address into a format that is easily processed by the machine learning model. The idea is to reduce the resolution between the data and scale down the data to make it lie between 0 and 1. Now let's look at the model itself. We use recurrent neural networks to capture sequential data, and we use a special kind of recurrent neural network called the long short term memory unit or LSTM at the core of our architecture. This reduces the vanishing gradients problem faced by typical RNNs that occur during backpropagation. So we also use linear layers along with the LSTM in our network. Note that for the classification network, the output size is same as the total number of load addresses possible, whereas for the regression network, there is only a single output which we can convert into the load address. Coming to the loss function, for the classification model, note that the output activation layer is the softmax function, and this ensures that the output is actually the probability corresponding to a particular load address. For this purpose, we use cross entropy loss function, which is very well performing for multi-class classification. For regression, however, we desire the input and output to be as similar, as close to each other as possible. So we use the mean absolute error loss function for regression. These are the hyperparameters for the classification model. We begin by passing the page and program counter inputs through embedding layers, which is followed by an LSTM, and finally a linear layer with a softmax activation function. The loss function is the cross entropy loss and the optimizer is Adam. This classification model worked well for page prediction. This is the regression model hyperparameters, and the major change is that the linear layer has only one output and there is no activation function. This worked well for offset prediction. Now we'll take a look at Voyager, which is a model that has been proposed in a publication from the ASPLOS 21 conference. This served as an inspiration for me throughout the project. It was a model that has been proposed specifically for prefetching. The idea in this model is more or less the same as the classification network mentioned above, with a lot of key exceptions. Firstly, it takes into account both the load address and the instruction pointer. It uses embedding layers instead of one-hot encoding. It uses a novel page-aware offset embedding layer, which gives context to the offset and makes the input data more meaningful. It also uses multi-label classification, which is possible because there is no single correct prefetch, and you can also prefetch an address that is 4 to 5 spaces from now. It uses multi-label classification depending upon different criteria. After a lot of experimentation, these are some of my observations. The regression models do not tend to give the right outputs because even small addresses would give us an inaccurate output that leads to a completely wrong prefetch. So as compared to a regression model, a classification model might be a better approach. However, the classification model has a huge address space and the model itself consumes a lot of memory footprint. Coming to the results, the models converged to local optimum, but they couldn't generate satisfactory results. Instead of giving accurate predictions that vary with varying inputs, the models tend to give the same output for any kind of input. I've also tried implementing the Voyager model, but it couldn't show satisfactory results. However, I've tried implementing classification model for page prediction and regression for offset prediction simultaneously, and the results were a little better. So this is a plot for offset address prediction. I have used regression here, and we can see that while there are a lot of inaccuracies, we can still see some good predictions which were better compared to the other models. This is the page address prediction using classification. The orange color shows you the predictions, whereas the blue shows you the labels. So here are a few plausible improvements. We can make modifications to the model to be able to learn and predict discontinuous patterns, as we saw in the input data. We can also train a model that learns when to prefetch, using the input data as the prefetcher and generating labels using the loss function of the prefetcher itself. Finally, this is the summary of my work. I started by learning the necessary theory that's required for this project that is related to computer architecture. Then I explored the trace dataset to find patterns in the input data. I read and understood the Voyager model, which served as an inspiration for the rest of the project. I also read some literature on sequence prediction and RNNs to understand them better. I also learned how to implement neural networks using the PyTorch framework. And then with the knowledge I accumulated, I recreated the Voyager model to understand the network better. I also trained and tested the model using the ChamSim simulator on a virtual machine provided by the institute. I came up with new ideas for possible efficient models, and which were the ideas for the classification and regression model. I trained and tested these models as well, and I've tried and tweaked the hyperparameters and architecture to improve the quality of the results. Throughout the project, I've used the PyTorch framework to develop the neural networks, and I have used the ChamSim simulator to feed the trace files into the model and to train them and generate prefetch files. The key takeaways for me in this project were learning a lot of things. I've learned how to use different frameworks, and I've used the foundation that I've learned in my course to learn more things that were beyond the scope of the course. An important takeaway is that I've learned how to apply domain knowledge to make machine learning models more efficient, and I think that is going to be a very useful thing. Thank you for listening.